Welcome back. So we had previously looked at the Carnot cycle and how the efficiency of the engine ended up only being 33% when we have a room temperature 300 Kelvin hot and a 200 Kelvin, so really cold cycle. Efficiency will only ever approach 100% if one of two things happens. T hot approaches infinity, such that the Q1 is Q3 divided by Q1 is essentially 0, or TC, the cold temperature reservoir, approaches 0 Kelvin. So 0 divided by any number is 0. If we can't have these two things happen, 100% efficiency can never happen. So we could hypothetically calculate our efficiency by just comparing the cold temperatures. As 200 divided by 300 is 2/3, and 1 minus 2/3 is 33%. Setting the 1 minus Q3 over Q1 to equal 1 minus TC over TH, we can remove the ones and get the TC and TH to the other side and cross multiply to get the Q's and only temperatures in the denominator and only heats, only heats in the numerator. So we can get that Q3 over T cold plus Q1 over T hot is equal to 0. Essentially, we can make that an integral, where essentially the integral of the heat of a reversible cycle over the temperature for the cyclic integral will give you 0. Now remember that that Q is not a state function; it's path dependent, and so because of that, it cannot have a definite integral. But in the case of highly defined state function, highly defined paths, we can get a definite integral. So for a reversible path, cyclic heat-based state function, where we divide by temperature, always equals 0, we get a stack differential. And this must be the state function that we're going to define as S, or entropy. If we do the integral of Q over temperature, we will get entropy. And this is all well and good for calculating reversible path function. But how would we calculate this for irreversible process? We can do that by getting a path independent ds, by solving ds by partial differentiation with respect to changes in the single combination variables of t and pv. Q is path dependent, but S, being a state function, how we define a state function, is always path independent. So for my crutch word, so the entropy of an irreversible process. If we calculate this for this path, we can calculate this in terms of our state variables Tp and V based paths. So delta S for T, our constant T is just integral of heat over temperature, Q over T. So, and when Q is isothermal, remember that heat of isothermal was the opposite of work, and it was a negative, so negative or negative makes it positive, nRT, ln VF over VI. And so when we divide that by T, the T drops out. We can also set that up to PV equals nRT, exchange P or V in such a way that this becomes a negative NR natural log PF over PI. In the case of delta SP, integration of Q over T. Now T is changing. But how would we calculate Q at a constant P? Well, we say, well, constant P, that's C sub P sub M dt. Dividing that by T, C sub P comes out. The integral of 1 over T dt becomes ln TF over TI. Same thing happens with entropy at constant volume. We can say that that's C sub V ln TF over TI. So we've defined 3 different paths we can take in any situation: constant S, constant T, constant P, or constant V. With that in mind, we can calculate entropy through any path of isochoric, isobaric, or isothermal by combining those 2 functions together. So the total entropy of a constant, we can calculate this over 2 paths: constant volume, constant temperature, or constant pressure, constant temperature. Just fine and dandy. By calculating 2 paths separately, you're essentially, if I got a point here and I have a point here and I want to calculate a straight line, what I'm doing is I'm changing one variable to get here, changing the second variable to get there, and combining those 2 together to get that hypotenuse. That's what we're doing as we're doing this partial differential. Allows us to calculate it for 2 variables changing at the same time. So, entropy of phase changes. We can do that just the same. Since we're looking at a reversible process, constant T, the entropy of phase change simply is the Q reversible of that phase change, which would be the heat of fusion or the heat of vaporization, divided by the temperature which this occurs, because the only time it's reversible is at the freezing point or boiling point. So you can calculate that for water. If I want to calculate the heat of vaporization, right there, the delta H of vaporization would be the difference between 285.8 and 241.1, 241.8 minus 285.8. So we get a positive 44,000. 44,000 joules have to be absorbed. And that occurs at 373 Kelvin. So multiplying by 1,000 to get that. So we get 117. Now delta S for that, calculating the traditional way, the gas 188.8 minus 70, it's about 118.8. Slight difference. Small difference, probably rounding from the temperature. Now, we can also calculate entropy for real compounds, especially solids and liquids with respect to T and P or T and V, where we know the beta and the kappa, but not the equations of state. So the next 2 functions are doozy. You'll probably want to wave your hands and just use them as given, not the proof. I'll attempt to prove them in the next couple slides and say that the T is just fine. But with the V, it's beta over kappa dV. Or we could do beta over, so making that a lot easier instead of the natural log. Or in the case of pressure one, it's V beta dP, where V is assumed constant and we go from PI to PF. So we're going to start from the different partial differentials of ds equals ds dt, and ds dv dv, recognizing that ds is also equal to dq over t. And that's also equal to 1 du over t plus pdv over t, because q is at constant pressure is enthalpy divided by t. And thus, enthalpy is also u plus pv. So we're going to plug these in and evaluate each of these separately. So let's go through that first before we go to the next step. This is a doozy. So we have q over t is equal to u over t plus p over t dv. That's also equal to our ds dt dt plus ds dv. Okay, we know what du is. We know what du is. Du is equal to du dt dt and du dv dv. We know this one is c sub v t. The other one, we're going to leave that as is for right now. So basically, du dv t plus p over t dv. Now, at a constant volume, these first two terms drop out. And so we get ds dt, we can divide both sides by dt, and we get that ds dt is equal to cv over t. It would be cv over t. So that makes ds dt cv over t. Now, when we instead look at the other possibility, where volume is allowed to change and temperature is allowed to stay constant, we divide both sides by dv, and we get that ds dv is equal to 1 over t p plus du dv. We found this guy earlier. Now we're going to actually prove that one. So from this point, this is where we're going to do that, get back to that proof. So I'm going to go back to the share. So we're going to use the proof that the state function proof that d over dx, dz over dy is the same as d over dy, dz over dx, and the chain rule to solve for the unknown differential du dv, which we will in turn use to simplify ds over dv. So let's go back to this. Okay. Go ahead and clear this. So, and just put up here, right now we have ds over dv is equal to this unknown not fully spelled out integral of du. That's where we have. Now, and we have ds t cv over t. So the state function says d over dt ds over dv must equal d over dv ds over dt. That's a state, the rule of state function. Plugging stuff in. For this side first, ds over dt is going to be our, let's see, so I'm just looking at my notes real quick. Okay, I'm going to just, even though we technically know this, we're going to plug this in. So this part, ds dt is du dt over t. So factoring out the t, that we have d dv du dt. So that's one half. The other half is because of this, factoring out the t for this guy. The product rule wants us to go 1 over t dp dt plus d over dt du dv. Okay. Those two things must be equal. Two things must be equal due to the product rule. So we can't just do that. We also have a secondary part. We could either do the inside part or the outside part. The product rule also includes this part. 1 over t squared, which is the d dt, and then this leaves the p plus du dv. So the product rule separates that t from the p du dv. And we switch those around. Okay. Send those two equal and multiplying both sides by t squared to get t's out of the denominator. Both sides by t squared gets us to this. And I'm going to evaluate as much as I can. So follow with me here. So you have t dp dt we have t d over dt du over dv. We have negative p, and we have negative du over v, du over dv on one side. On the other side, we have t d over dv du over dt. Now we're going to try to simplify this. If we already stated that if d over dv du dt, since u is a state function, is equal to d over dt du. If u is a state function, then this term cancels out with this term. Those are the same, and I can subtract those out. With that in mind, getting du dv on the other side, we get du dv must equal t dp dt at a constant p minus p. So there's our du dv. We kind of done that before. We kind of skipped some steps to get there. But with that in mind, so putting that back in to our ds dv comes remember our ds dv was 1 over t p plus du dv. So plugging that in for du dv, p's cancel out. The t's will cancel out. So we have ds dv is just simply dp dt at a constant. So this difficult integral ds dv becomes this easier integral of dp dv dt. And we formerly proved that dp dt is equal to beta over kappa. So ipso facto, ds dv is equal to beta over kappa. So this proof, we could have waved our hands, but it's there to show us both parts, how we got du dv, but also how we get ds dv. So similarly, if we wanted to do ds dp, we'd have to do the same thing with du is equal to dh minus pdb or vdp, and it's going to simplify down to the dp dropping out. And so that equal to tds minus pdb. I'm going to skip this proof, but it's essentially the same thing, and it's the same way, and we're going to get dhdp in the process, which we already kind of showed. But from there, if you follow the steps back with something we already proved, we can get that negative v beta would be our ds dp. I'm going to skip that. Save ourselves a little bit of trouble. With that in mind, we're going to go ahead and try to do some problem. 1 mole of oxygen is kind of already have the work shown out, so I'm going to make it a little bit easier. 1 mole of oxygen is heated from 200 Kelvin at 1 bar to 500 Kelvin at 7 bar. What is the change in entropy? So remember that ideal gas ideal gas beta is 1 over V dB dt. And thus, dB dt at a constant pressure is going to be 1 over T. So we're looking at, I know too. V is equal to nRT over P. You remove the T, and then you put the V back in. You have PV equals NR, so we're only missing the T. So that exchanges for 1 over T. So C sub P is actually this function. Now, this is one of the first times we really see this in practice. But C sub P for a gas is often a function of temperature. So it's not just, we kind of saw that in some of the problems of last chapter, but now we get into it here again. It's not just always a constant number, it's actually a function of temperature, and so you have to integrate it with each individual value. So, and these are just constants carried out. Now, because this is delta S is C sub P over T, and this is V beta over P, so it's volume over temperature dP. So this becomes what, 32.83 over T. Point T over T is 1. T squared over T is T. T cubed over T is. So as we integrate this, this first number is going to be ln Tf over Ti. The second number is going to be just delta T. This third number is going to be T squared third number is going to be T cubed and to make this in terms of beta, V over T is equal to NR over P. That's just going to be ln PF over PI. NR, of course. And so let's do the easy part first, the pressure. So negative 8.314 natural log of 7 over 1. So the entropy goes down, which you would expect, by 16.17 from the pressure change. Each term of the temperature is going to make this go up. So 32.83 comes natural log of 500 over 200. 30.08. Next term, negative 0.03633 times 300 minus 10.9. 1.1532 times 10 to the negative 4th divided by 2 times 500 squared minus 200 squared. So that's going to be a positive, adding a positive 12.11. Last one, 1.2194 times 10 to the negative 7 divided by 3 times 500 cubed minus 200 cubed. So that's negative 4.76. 30.08 minus 10.9, 12.11 minus 4.76. So the temperature change results in a net increase of entropy of 26.53. The pressure change decreases by negative 16. So the net entropy change is 10.36. 10.36. So all things considered. Not a big change, but a change nonetheless. Last thing, 2 moles of liquid carbon tetrachloride are transformed from 298 Kelvin at 1 bar to 343 Kelvin at 5.2 bar. What is the change in entropy if beta is this real number instead of a function, and density is this, and so we have to convert our pressure into a volume. Get this number. So C sub P dt. C sub P is 133.9 joules per mole Kelvin. There's 2 moles times natural log of, because we integrate 1 over T, 343 divided by 298. So the entropy change from the temperature change, entropy change is 37.6. So at 1 bar, the density, so we have 2 moles. The density of carbon tetrachloride. So 2 moles divided by the molar mass, which carbon is 12. Chlorine is close enough to 35.45, and there's 4 of them. So actually, okay, I did that wrong. Okay, so 2 times the molar mass, we have 307.6 grams. The density is 1.59 grams per centimeter cubed. That means we have 193 milliliters. Turning that into a volume of liters, that by 1,000, means we have 0.193, so 0.193 liters times beta, which is 11.4 Kelvin. So 4 times 10 to the negative 4th Kelvin times our pressure, which goes from 5.2 to from 1. Okay. So for a really small number, so bar liters per Kelvin. So then there's 100. If I did this right, the change from that is only 0.092. 37.66 minus 0.0926, 37.56, if I did that right. Okay. Yeah. So, of course, that's not a really big change at all. But let's think about this. What does that mean? What does all this mean? We have a liquid carbon tetrachloride, which is why we're not using the ideal gas equation. So, ideal gas, you will change a lot when you put pressure on it. A liquid often has very little change when you put pressure on it. And so, even though this is being compressed, the entropy change is very, very little. The biggest thing is the motional change of heating it up. These guys are allowed to ricochet around in the liquid container. Even though I'm putting pressure on it, it's not causing a very large effect because this is looking at the pressure of a pure liquid. Okay, that's where we're going to stop for now. I'd like to thank you, and please like and subscribe.